For what it's worth, we won't need to dip into molecular orbital theory to explain most geometrical arrangements of most atoms in a molecule. Instead, we're going to use a method which is familiar to you from general chemistry, which is VSEPR theory. VSEPR here stands for valence shell electron pair repulsion theory, and it states that the local geometry of an atom can typically be predicted by using the steric number of the atom and assuming maximum separation of electron groups around that atom. Here, steric number is the formal term for something that we usually in general chemistry call electron domains or electron groups or something like that. All three of these terms refer to the same thing, which is the number of bonding and or non-bonding domains around a single atom. Let's take a look at some simple organic examples to see what we're talking about here. Specifically, we're going to take a look at methane, formaldehyde, and acetylene. The first thing we want to do is determine the steric number around each of the atoms in the molecule. This is the same thing you did back in general chemistry when you counted the electron groups around an atom. Remember that multiple bonds only count as a single domain or a single group around an atom. So this means that methane, its carbon has 4 electron groups, a steric number of 4. In formaldehyde, both the carbon and the oxygen have steric numbers of 3, and in acetylene, both of the carbons have steric numbers of 2. From this, we can assign hybridization states. A good rule of thumb, or way to remember how to do this, is that the steric number is the same as the number of hybrid orbitals you need. So 4 electron domains, 4 electron groups, means we need 4 hybrid orbitals, 1s plus 3 p's, sp3. For a steric number of 3, these are sp2, both the oxygen and the carbon in formaldehyde are sp2 hybridized, and for acetylene with its 2 electron groups, both carbons would be sp hybridized. Finally, the hybridization state of the atom corresponds to a particular VSEPR shape. sp3 atoms are tetrahedral, sp2 atoms are trigonoplanar, and sp atoms are linear. The bond angles associated with this are about 109.5 degrees for tetrahedral, 120 degrees for trigonoplanar, and 180 degrees for linear. Now let's try drawing what these would actually look like. Let's start by drawing methane. This is what our tetrahedral methane would look like. Remember that for a tetrahedron, we always have 2 bonds which are in the plane, 1 bond which is going back, and 1 bond which is going forward. We need to be the most careful with drawing tetrahedra because this is a 2-dimensional projection of a 3-dimensional object. This is not the only way that we can draw a tetrahedron, but we will always have these 4 types of bonds in some arbitrary orientation. Here, for instance, are 2 drawings of the same molecule shown from different orientations. Note how I've oriented the molecules differently, but that orientation is arbitrary. We could even orient the molecule like this, and this would still be a correct drawing of a tetrahedral atom. For formaldehyde, the molecule is trigonoplanar, meaning that we would draw it like this. Note that there's more than one way to draw a trigonal plane. We can also draw the trigonal plane as coming in and out of the page. So again, these 2 drawings are of the same molecule, but they are shown in different 3-dimensional orientations. Finally, for acetylene, well, that's just how the molecule looks. It's already been shown with the correct orientation. One thing I would highly recommend here is use your modeling kit to build all of these molecules, and then try to align each molecule with each 2-dimensional representation. Translating between the 2-dimensional representation and the real 3-dimensional form of the molecule is a skill that needs practice, and the earlier you get this practice, the better for some of the topics we're covering later in the course. Now, for the most part, the molecules that we're going to encounter in organic chemistry have a lot more atoms and are a lot more complex than the ones we've just seen. So we need to be able to carry out this procedure for a molecule which has many atoms, many of which may have different 3-dimensional geometries. Let's take a look at a fairly common type of molecule, or a molecule showing a lot of the geometric features that we need to look about, which is this one here. Now, to draw the 3-dimensional shape of this molecule, we're going to follow the same procedure. We're going to start by finding the steric number of each atom, assigning the hybridization state of each atom, determining the local geometry of each atom, and then finally we're going to draw the molecule by building it 1 atom at a time. This is the same process we talked about in the molecular orbital video, where we treat the molecules like Legos, like little building blocks, and we build them together 1 piece at a time. So let's walk through this example. First, we have 3 tetrahedral sp3 hybridized atoms with 4 electron domains. We have two trigonal planar sp2 hybridized atoms, each with 3 electron domains, and we have two linear sp atoms, each with 2 electron domains. Here I will color code these so that we can keep track of which atom is which. Now that we've done that, we have all the information we need to build a 3-dimensional model of this molecule. What I'm going to do is I'm going to pick a starting atom, which can be any atom in the molecule. There's no rule about how you have to do it. I'm going to build the local geometry of that single atom, and then I am going to attach these atoms one at a time, building from that part, keeping in mind the local geometry around each. So let's take a look at how we do this. Let's start with the carbon atom on the left, which is tetrahedral. I draw that carbon atom in the tetrahedral form, and then I fill in all of its neighbors. The next neighbor I get to is a trigonal planar atom, so I fill in its geometry and its neighbors. And then we continue to build from there. We fill in the lone pairs on the oxygen, and then I can move to the next carbon, which has linear geometry. Then we move to the next linear carbon. Then we have another tetrahedral carbon, so we fill in its neighbors. Now we're finally at the tetrahedral nitrogen, so we fill in its geometry and all of its neighbors. One small piece at a time is how we can accurately draw the 3-dimensional geometry of the whole molecule. What I'd highly recommend here is to build a model of this molecule and twist and turn your model around until you can find the correct alignment with how we have drawn this on the page. Let's do a little bit of practice. What I'm going to do here is I'm going to show you 3 molecules, and I want you to draw a plausible representation of them showing accurate 3-dimensional geometry. First, we have this molecule here. Now, a note about how I've shown this. The groups on the ends are shown in what's known as condensed structural formula notation. What this means is that we have a carbon which is bound to 3 hydrogens, so the bonds are not always going to be shown explicitly. Here's another molecule that also has the condensed structural notation. And then finally, here's one that shows a bit more complex condensed structural notation. There's 2 features to explain here. One is that the brackets here indicate a group which is repeated. So here we have 4 repeating CH2 units connected to each other. And this big thing on the top indicates that the 2 atoms connected by the bracket are connected in a ring. So based on what we've shown and discussed here, draw plausible 3-dimensional representations of these 3 molecules. You can build models if you want to help you out. In fact, I would highly recommend that. Pause the video and take as much time as you need here, then I'll show you how I drew them when you're done. Let's start with our first molecule on the top left. Here we have 2 tetrahedral CH3 groups at the end of the molecule connected to trigonal planar nitrogens and a linear carbon in the center, so we'd end up with a drawing like this. For the second molecule, this is one way to plausibly represent the 3-dimensional geometry of this molecule. Here we have a lot more tetrahedral atoms, so things get a little more complicated. Then finally, the molecule with the ring, we have 6 atoms in a ring. We've shown 1 and 6 explicitly. Atoms 2 and 5 are inside the brackets, so we'd end up with something like this. Again, I really want you to try building models of these so that you can really get a sense of the real 3-dimensional shape and size of these things. Another thing to note is which parts of these drawings are the easiest to line up and which are the hardest. If you can recognize which parts of the molecule are the most difficult to draw, you can often start with those parts and save yourself a lot of time later. Next, what we'll be doing is we'll be doing a brief review of intermolecular forces and solubility.